So firstly, I want to thank Anil sir for inviting me to this webinar. And so today in this webinar, I'll be mainly focusing on the modeling and simulation with LAMMPS rather than the theoretical knowledge of classical molecular dynamics. So I think instead of being a very formal webinar, I want to make it a bit casual so that the students can ask me questions whenever they want, and I'll try to answer all their questions. So welcome to the webinar of modeling and simulation with LAMMPS, and I'm Abdullah Rafat. And so about me, I'm a senior year undergraduate student, and I'm studying material science and engineering at Khulna University of Engineering and Technology. And my contact info is given there. So if you face any problem, you can mail me, or you can go to my LinkedIn or wherever you can message me through there if you face any problem in future. So I think you already know the overview of LAMMPS, but I still want to address these things. So LAMMPS is mainly a large-scale atomic molecular massively parallel simulator, which mainly deals with the classical molecular dynamics, molecular statics, and Monte Carlo simulations. And there are multiple processes to run LAMMPS, that is serial execution, parallel execution, and GPUs. So serial execution actually works with a single processor. So suppose you want to run a very small simulation, so you can use your one processor computer so to run the simulation. But suppose you're working with a large scale simulation, and you cannot run a large scale simulation with your single processor. It may take like days and days, maybe a week or maybe more than that. So in those cases, we use parallel execution. Mainly, suppose you have an workstation or maybe an HPC, then you can use parallel execution to run those simulations, those large scale simulations. And GPU is just an extra part, so that you can use also your graphics processing unit to run the simulation faster. Okay. So LAMMPS works in a lot of interdisciplinary sections, like it works with atomic particles, then granular particles, and biological molecules, crystalline structure, then polymers, and all those. It mainly works on the dynamics of atoms. And after that, I've written the comment to run LAMMPS on terminal, or maybe a command prompt if you're using Windows. So I think you already know all this, but still, just for the presentation, I have written all those. And there is also to find mainly the force field potentials. I have written a website, so NIST website, that is the National Institute for Standard and Technology. So you can find a lot of potential, mainly EAM and MEM potentials there to run your simulations. Okay. So today I'll be mainly focusing on two simulations. One is the 2D flow simulation, and the another one is a aluminum tensile loading. And after that, from the aluminum tensile loading, we'll be generating a stress versus strain curve, and we'll be calculating the elastic modulus from the stress versus strain curve. Mainly the 2D flow simulations are honestly advised me to make a simulation like that, so that putting a thermostat and giving up. Okay, let me start, then I will show you. So firstly, I want to talk about the 2D flow simulation. So this is mainly Anil sir told me to make a script about this one, so that in a structure where there will be a velocity on the upper layer, that the upper and the lower layer, those are rigid layers, and the upper layer will be moving in the right direction, and the lower layer will be moving the left direction. And in the middle layer, it's there will be the equilibration. Those molecules are deformable, so that the thermostat region will be there, and those molecules will move, but the top layer and the lower layer will be rigid, and there will be a downward pressure from the top. Okay, so this is the first simulation we'll be doing. So, okay, so a bit from the context that you already, I think you already know that LAMMPS works on the classical molecular dynamics principle, that is the Newtonian mechanics. So I will not touch those parts. I'll directly go to the script, how to write scripts, and how to sectionize those scripts to run the simulation for better understanding. So to write the input script in LAMMPS, you have to take 4 steps. The first one is the initialization. The second one is the system definition. the third one is the settings, and the fourth one is the simulation execution. So mainly the initialization part has the units, the dimensions, the boundary conditions, the atom style of your simulation, or maybe how you need to clear those memories and maybe some extra variables. That means the initialization part actually initializes the simulation, how to run the whole simulation in the later stages. Then comes the system definition. So mainly in the system definition, you will be defining the whole system, the atomic system. So suppose you are having a FCC lattice structure. So in the system definition part, you will be having the lattice commands, which will define your lattice structure. Then the region commands, how we will define the region of the system. I'll be discussing those also later, but this is just a total overview. And then the groups, then creating atoms, then the mass, then setting its charges, setting its mass, and all those properties of molecules or atoms. Then comes the setting part. So this is one of the important part, the setting part. In the setting part, what we do is we define the force field. That is the pairwise coefficients. So suppose you're using a Lennard-Jones potential, or maybe a EAM or MEAM potential. So in this section, you will be defining those potentials for your pairwise interaction of atoms. And the neighboring list, I think you are familiar with the neighboring list. That neighboring list is listing a specific neighbor of atoms to reduce the computational cost. Okay, I will be discussing that later. But so this is the main settings part, that we will be defining our force field in the settings part, and we will be defining the computes and variables. I mean, what you want to calculate further to in the settings part. And after that, the main segment, that is the simulation execution. In the simulation execution, we'll be defining the fixes that are based on the simulation. I mean, how the simulation should react. Those will be in the fixes, and the outputs, I mean the dump output, to visualize the simulation and to get the data's output. And there is also fifth section, that is the post-processing section, which we don't do in LAMMPS, which for those reasons, for the post-processing part, we usually take Ovito, or maybe we use base Python programming, or maybe other programming languages to analyze those data. So at first, the initialization part that we have talked about. So the simulation we are doing here, let me remind you again, the 2D flow simulation. So the first thing is dimension of flow simulation. Okay. So the first command should always be clear. So clear is actually what it does is delete all atoms and restores the setting to the default value, and also freeze all the memories by LAMMPS. So why it is used mainly? Suppose you ran a few simulations further before running this one. So there might be some memory allocation in LAMMPS that may affect the new simulation you did. The new simulation you're doing might have some effect on the past simulation. I think, sir, there is a bit of noise. I mean, can that be reduced? Okay. So then comes the unit. So we are clearing all the memories. This is the first part. We are clearing all the memories allocated in LAMMPS. And then comes the second part, the third line. You can see units. So in this simulation, I'm using the Lennard-Jones unit, which is the default unit in LAMMPS. But in most of the cases, in most of the real life simulation, we don't use Lennard-Jones. Rather, we use metal real units. These are the most popular units, but you can also use SI units. So what are the differences? So as you know, Lennard-Jones unit is very, it doesn't have a specific unit value. I mean, like dimensional values. Whereas if you use like Lennard-Jones unit, the distance is angstrom and force is electron volt per angstrom. Whereas for real unit, the distance is same angstrom, but the force is kilojoule per angstrom. Whereas for SI unit, the distance is meter, and then the force is Newton. We all know those. And you will get all these things, the values, the specific values of units in the LAMMPS documentation. If you search the LAMMPS documentation, all the units are given, and what are the respective values of those units are also given there. So that is the unit part. And one more thing is that after you define the unit, you have to write the whole simulation based on that unit. So suppose you are using a real unit and you cannot use a force based on a metal unit in the simulation. That will change the values. So you have to use suppose you have a paper based on the metal unit and you want to do a simulation real unit. So you have to convert those values from metal to real to run the simulation. Okay. So, and about the dimension, I think you already understand what the dimension is. So it's a two-dimensional simulation. As we are doing a two-dimensional, it can be 3. So actually the default value is 3. So if you don't write this the dimension 2, then LAMMPS will take the total dimension of the simulation as 3-dimensional simulation. Then comes the boundary condition. So there are mainly 4 boundary conditions in LAMMPS. That is P, S, F, and M. So P is a periodic boundary condition, S is shrink wrapped, F is fixed, and M is a mixed boundary condition. So the most popular is the periodic boundary condition, as it reduces the computational power. I think you know about periodic boundary condition, that suppose this is atom, then the same atom will be expanded throughout the simulation in the same position. I mean, suppose this is our total unit, total simulation box. So this simulation box will be expanded throughout the space in the same way. So the way it reacts, the other boxes will react the same. So you don't have to calculate a large box. Rather, if you calculate specific section, then it will already be calculated. And then comes the fixed. I think now you understand the fixed boundary condition, that the fixed is the simulation box is the value of the simulation box is fixed, so it will not change its shape. And the shrink wrapped is that wherever the atom goes, the simulation box will change itself. So suppose due to some simulation, I mean, like suppose you're using a diffusion simulation, or maybe some vapor gas simulation, maybe. So what happens in the vapor simulation? Suppose the atoms are flowing and you need to expand the simulation box up to a certain limit so that the atoms can flow up to that limit, suppose. But suppose you are using a fixed simulation or a periodic simulation. So what will happen if you use a periodic simulation? The atom will go out of the box and come from the back. I mean, suppose that if the atom goes from the top of the box, it will come back from the bottom if you're using a periodic boundary. But if you're using a shrink wrapped, the atom on the top will go as far as it can, and the boundaries will go with the atom. So the boundaries are changing. So that is the difference. And so why we are using S? I mean, we're using a S in the Y direction. So here you can see I have used the boundary condition for PSP. So P means periodic in the X direction, S in the Y, and P in the Z direction. As the Z direction, I'm considering the Z direction is a two-dimensional simulation. So the Z direction doesn't matter. But why we are using a S in the Y direction? That is because we are using an extra force. If you can see, here you can see that we are applying a downward pressure on the top layer. So if you are using a fixed boundary condition, then the layers will be fixed. So that will not be a correct simulation. As we are using a shrink wrapped, I mean S on the Y axis, so the boundaries, the Y boundary will change as per the pressure provided on the top layer. So that is why we are using S on the top. I mean, sorry, the Y axis, S on the Y direction. Okay. So then the atom style, you can see the atom style is atomic. So about this part, there are multiple atom style in LAMMPS. Atomic, then bond, then charge, full, sphere, and many other. So what it does is it defines how the atom should be. So that is its default value is atomic. Okay. So that is, suppose you were using a charged particle. Suppose you are using an atom with charge. So then you have to define the charge of the atoms, right? Then you will be using the atom style charge so that you can define the simulation properly. And suppose you have some bonds in the atoms. I mean, a bond between atoms. Suppose you are using H2O. Okay, so H2O must have some bonds, right? So in that case, you must use a bond or maybe a full to define the atom style, because otherwise, if you use the atomic style, then it will not calculate the bond values or the charge values of those atoms. Okay. So the next part, the second part is the system definition. Okay. So what I said earlier, system definition, what it does is actually it defines the simulation box and creates all the molecules in the simulation. So I'm mainly defining the total system here, right? Okay. So the first thing, so in the 10th line, you can see I've defined the lattice command. So this is actually the command, and this is the values. So I'm defining the lattice command and hex 0.7. So hex is actually hexagonal. That is 2D hexagonal lattice, and 0.7 is mainly the lattice constant. And important thing to note is that I have mentioned that in this simulation I'm using a LJ unit. So this 0.7 will be in the LJ unit. So I have defined the lattice, how the lattice should be formed, hexagonal lattice, and 0.7 lattice constant. In 2D, there are mainly two types of lattice. That's one is hexagonal and this one is square, as far as I can remember. And for 3D simulations, there are like FCC, BCC, and then there are SC, which is a simple cube, and HCP. And also there are systems like you can define the basis of the lattice by yourself and then do the simulation. You can find all those in the LAMMPS documentation. And then I'm defining a region. So the most important part here is the region, the first region. When we're defining the first region, it is defining the total simulation box. So here the first region is region, and then box, block. So these values, okay. So this is the region values, and box is the name of the region. So that means I am defining a region and I'm naming that region as box. Then a block type region. So a block type region is more likely a rectangular region. That is the angles of 90 degrees. So a block type region. And then I'm giving a x high and x low value. So this is the x low value, that is 0, and x high value, it is 20. So this is mainly the simulation. So along x-axis there will be the 20 length, and along y-axis there is 10 length. That is y low 0, y high 10, and z low minus 0.5, 0.25, and z high 0.25. So that is the case here, and the name of the region is 1. So z, there is 1. So z actually doesn't matter here, but I'm defining a z value because suppose I want at least one atom to be in the z value. So if I don't define the z value at all, then there will be no atoms there, right? So that is why I'm defining a z value. So I've defined the region, and now the next part is the create box. The create box, 3 boxes. Okay. So this is mainly I'm creating multiple boxes in that box region. So remember, always the first command of the first command after the syntax. So these are the syntax, and this is the first command. Usually the first command are always the names. So I'm defining a name that is a box, the name of the box, which is a region, and I'm creating 3 boxes in that box region. So suppose suppose you created a box and name it a sim cell or something, like suppose you're named sim. So when you're creating a box and put a 3 here, and then you have to write sim here, because the name of the region was sim. Okay. And here, as it is the name of the region is box, so I'm defining the create box command as 3 box. And why 3? That is because I'm using a 3 atom types, right? So here you can see like there's a top atom type, and there's a middle atom type, and there's a bottom atom type. So I'm using a 3 atom box at 3 atom type. So that is why I'm using a 3 create box commands. So actually what it does is actually it creates 3 boxes. It actually doesn't create an atom type, rather it creates boxes. But in turns, when you define the simulation, you work with I mean you define those atoms in those box types. So that means ultimately it defines your atom type. So then create atoms, one box, that is I'm creating one type of atom. I'm the first type of atom. So there are three types of atoms, right? 1, 2, 3. And I'm creating one type of atom throughout this region. So that means the first atom type will be covered in the total region. That is what I'm doing here. Okay. And then I'm defining the masses. Mass 1, that is 1, and mass 2 is 1, and mass 3 is 1. These are just random values. You can, when you are working with practical simulation, you have to write the real values here. So and again, one more important thing, that these are all Lennard-Jones unit. When you are working with the real unit or the metal unit, then you have to change these values based on those units. Okay. Now the system definition. We will be defining the total system into mainly 3 segments. There's the upper layer, the lower layer, and the flow region. So I've illustrated it here, that this total is the infinite value, and this is the infinite, this is infinite, this is infinite. So that means the high lows are infinite values, and Z is always infinite, as this is a 2D simulation. And now you can see, so if I want to define this much layer, what should I do? I should define a region, this specific region, and say that this region contains the second type atoms, right? So I have already defined a region that contains one type of atom, type 1 atom. And now I have two atom type 2 and atom type 3. So I have to specify that this region has atom type 2 or maybe atom type 3, whatever. But I have to specify this region, right? So how can I do that? So suppose when I'm defining the lower region, okay? So lower region should be more likely starting from, so consider Y. It is changing, the values is changing considering Y. So this should be more likely from 0 to Y equals to 1.25, right? So this region will start from 0 to 1.25, and along X, this should be infinite. So because this is an infinite value, right? So this is periodic, these will be infinite values, but along the Y, there is a finite value from 0 to some value. Suppose that is a 1.25. So that is what I did here. You can see that for the first region, 1 block. So again, this is the name of the region. It doesn't mean anything, but this is just the name. And later when we call the region, we have to call by its name. So region 1, again a block type region, there's a rectangular type region, and then infinite. So these are X low and X high, which are infinite values. So like infinite and infinite. And then in the Y low and Y high. So Y low, we are giving an infinite value, and then for Y high value, that we are giving 1.25. So from lower total to some portion like 1.25. And then in the Z axis, that is total infinite values. Okay. So that is what we did here. So we have defined that lower region, and we name that region 1. And then we are defining the upper region. So similarly, the upper region starts from 8.5 and ends with an infinite value. Okay, so the same thing, the total top part. So that is X low, X high, infinite, and then again Y low is 8.5, and then Y high is infinite, and then the Z value is always infinite. So now we are defining that region to a group, and why we are doing this is because when we provide a fix to those certain region, we need to consider it in a group, or else we won't be able to provide fixes on those regions. So that's what we did here. So we have named the group lower on the one region. I mean, this is a group lower. So at first it was region 1, but lower group. So the lower part, its name is region 1, but its group name is lower. Again, so this part, the region name is 2, but the group name is upper. And then I have defined another group, that is the boundary union lower upper. That means that why we are doing this, we are defining the boundaries. So these two are the boundary, right? These two are the boundary. So we're just saying that upper and lower equals to boundary. So we're defining another group so that if we provide some fixes on the only on the boundary group, then we don't have to write two fixes individually on the upper and lower groups. Rather, we can just provide a fix on the boundary group and it will fix the upper and lower group. And then we are saying that flow group, which is subtract all boundary. That means the flow group, which is the middle one, that will be the all atoms minus the boundary atoms. That means all atom minus upper atom minus lower atom. Okay, so all atom minus the upper atom minus lower atom. So that will be the flow group. And now what we're doing is like we're saying that the upper group will be second type atom, and the lower group, sorry, the upper group will be third type atom, and the lower group is type 2 atom. So that is it. So that is how we are defining the system. That we are defining, we are subdividing it into 3 groups and then giving it different names. So this is the mainly system definition. And now comes the settings part. So as I've said earlier, that the settings part usually works for the force field, the neighboring list, and if we want to value some computation variables. So here you can see that for this simulation, for this specific simulation, we're using Lennard-Jones, and these values are actually arbitrary. So if you are using, again, I'm saying if you're using a real life simulation, then you have to change these values. I will be showing you a aluminum tensile testing simulation. In those simulation, I will be showing real values, but here this is just arbitrary value. So Lennard-Jones cut, the same thing. So the pair style is a Lennard-Jones. So suppose you're using a EAM, then you'll be writing EAM, and suppose you're using a EAM/alloy type potential, then you'll be writing EAM/alloy. And there are MEAM, there are UXFF, there are tertiary potential, and there are many more types of potential you can use here. And then this is the global cutoff value. I think you already know that Lennard-Jones potential needs a cutoff value, so that within that cutoff value it works, and after that it doesn't work. Okay, so that is the cutoff value. That's the global cutoff value. And you can also provide a local cutoff value, but that's not needed actually, as I've already provided a global cutoff value. And these are the coefficients. So here is just star means that it will work on every atoms. I mean, the interaction between all atoms to all atoms, the pair is interaction of all atoms. So suppose if you write here, wait, where's my mouse? Yeah, okay. So suppose if you write here 1 and 2, so that will be that the pair coefficients will work only on the 1 and 2 types of atom, type 1 and 2 atom. Okay, but when I'm writing star, that means it will work on all 3 types of atom with all 3 types of atom. So each has a value of 1 1 with each value, with each atoms. So the first value is the epsilon value, and the second value is the sigma value, which are parameters of Lennard-Jones. And then the neighboring list. I think you already know about the neighboring list, that it specifies a specific neighbor when to calculate the force, and when the atoms go out of the neighboring list, then it re-specifies the neighbor to calculate reduce the computational cost of the system. So here you can see so bin is the system, and then the 0.3 is the skin value, which is based on the distance unit, which is the skin distance of the neighbors. And the name modifier that defines the delay 5, that means it will create new neighbors every 5 time steps. And then comes the variable and compute. So these are actually optional. If you want to, suppose if you want to calculate the values of a specific group or a specific thing, or suppose you want to calculate group values of some random atom for something, so then you have to compute those and then output those. So that is why we're using a variable comment. So here you can I'm calculating the temperature of the flow group, which I named mobile, maybe like it's a mobile group, right? So it can move, so that was I'm like saying mobile. And so this mobile compute will calculate the temperature of the flow group. Okay, so and then I'm also defining a variable. The variable is the same as any programming language we work, that is a niter equals to 30,000. So niter, that means I'll be using this variable later for the run command. so that I can say how much iteration should the system work on. Okay. Then comes the thermodynamic properties. So these are the thermodynamic properties I want to see as an output. So thermodynamic 500, thermo 500, that means the skin, I mean, the output will be shown each 500 steps, and the values are, so these are custom value. If you don't write this, then it will be showing you a basic values of thermostyle. And then as I have written custom, so it will be showing the step, the number of steps that the simulation ran, and the temperature of the system. Then C mobile, so that you can see I have computed the temperature of the flow group as mobile. So I'm writing that this is a compute value. So this is how you write computes. So then the mobile, so this will give the values of the mobile group, how the temperature is changing in the specific flow group. Okay, so and the mobile is the name of the compute. Okay. So K is the kinetic energy, P is the potential energy, and volume, pressure, density. Okay. So now come the fourth part, which is the simulation execution. So mainly in the simulation execution, what we will be doing is we will specify the parameters that we told earlier, how the simulation should act, the whole system should act. So the first thing is the time step. You can also define the time step in before maybe in the initialization, but it's totally up to you, because time steps should be continuous throughout the simulation. So I have given it like 0.003. Again, this is in a time unit, and as this is a LJ unit, so this will be in the time unit of LJ. And I am setting the time unit to 0. That means it will start from 0. And why we need this? If I give you a slide, I mean like a slide idea, that is, suppose if you run, sometimes we need to run minimizations on the simulation to minimize the structure and then work with it. So when we run the minimization, then it already expands some values. I mean, suppose you ran a CG minimization for like 10 to 15 steps, then the whole simulation will start from that 15 steps and forward. But for the sake of calculations, it's very tough to know and when the minimization ends, right? So that is why we usually reset the time step to so that we know when the calculation started, when the main calculation started, rather than the minimization. And now then the initial velocity. So remember, we specified 3 groups: the flow group, the upper group, and the lower group. So the so I'm creating 3 velocities here. So this is the initial part, initial velocity that I'm providing. So the velocity of the flow group I'm creating is almost at 1 Kelvin. So this is the name of the group I'm creating the velocity for. And this value is a seed value. It doesn't matter. Seed value is whatever you give. It's a random seed value. So this is the, so that means this total flow group, the middle group, it will start with a 1 Kelvin value. It will start with a 1 Kelvin temperature value, and you know, like the temperature is related with force. The velocity. So creating a 1 Kelvin temperature on the system will create a velocity. So it will create a velocity in the flow region, and then the velocity lower set -1. That is what we are doing, is we are setting a velocity in the lower region as a -1. That means it will go along. So this is a Vx, Vy, Vz. So Vy, Vz is 0, and the Vx is -1. So this will move this side. You start moving that side, okay? And the upper is the same. So 1, 0, 0, x, y, z, Vx by Vz. So Vx is 1, and so this will move that side. So I've already provided initial values for upper and lower region, and then the static fixes. So I already told you the top layer, upper layer, and the lower layer are rigid, right? Rigid layers. But again, the upper layer can move with the pressure. Mainly, there is a pressure on the upper layer, though it's rigid, but there is a pressure, right? So that's why the first thing would be, we will be setting all the forces of the lower region as 0. So that is what we did here, that fix 1 lower, set for 0, 0, 0. So 1 is again the name of the fix, and lower is the group of the fix. Then set for 0, 0, 0. So f x, f y, z is 0. And then we are saying that the upper group is also rigid, but on the y direction it has a null value. That means if you provide some value, then it will take a value, but specifically it has a null value, so it will not move along x or z, but it can move along y. So that is what we did here, that we named the fix 2, the upper set force 0, null 0. So that is what we did here. And then fix 3, that is upper average force, AV force 0, -5 0. So -5 means, you know, like from top to bottom. So so the upper layer will be having a force -5. So you can also calculate the pressure from here, right? So as we are applying force from the area is pressure, so we all know that. So you can calculate the pressure on the top layer and provide this value. And again, this value is Lennard-Jones unit, and if you're using a real unit, then you have to provide according those pressure. Okay. So this is actually providing an external pressure on the upper layer. So we have already provided these values, that the fx, fy, fz is 0, then vx, vz, these values, and these values already provided here. And again, there another part, that is the we are working now with the flow part. We have already finished working with the upper and lower part, but we didn't work with the flow region, right? So now we will work on the flow region. So for that, we'll be using a NV ensemble throughout the simulation. I think you already know what is NV ensemble. So we are using an NV ensemble for the integration part, and for the flow region, we are using a thermostat, that is the temperature rescaling thermostat. Again, maybe you may use a Branson thermostat or maybe Langevin thermostat. There are also NVT thermostat. There are multiple thermostat to use, but here I'm using like the temperature rescaling thermostat. So here you can see that 200 1 That means 200 means it will update the temperature every 200 time step, and 1 that means 1 Kelvin and 1 Kelvin. So it will start with a 1 Kelvin value and end with a 1 Kelvin value. So that means it will equilibrate at 1 Kelvin. Okay. Sorry, I'm again saying 1 Kelvin. It's not in 1 Kelvin. It's actually in Lennard-Jones unit. I've written it mistakenly. I'm really sorry. So it will be more like in the Lennard-Jones 1. Okay. So and then 0.02 and 1. That means 0.02 is the window and fraction. Okay. So this means, so this is having a 1 Lennard-Jones temperature value, and when the window value is when it changes its temperature 0.02, it will recalculate its value to 1. So that is the window value. And what is the fraction value is it can change up to 1. So that means suppose 1 is here and it somehow reduced to 0 for some reason, we don't know, then it can change its value to 1. I mean, it can change its total fractional value to 1 and recalculate it. So that is the total meaning of this thermostat. And then other fixes, this is the important fix, that is all enforced 2D. As we are using a 2D simulation, so these mainly zero out all the velocity and forces along the z-axis, this z dimension. Okay, so if you're using a 3D simulation, you don't have to write this one. And then the dump output. So dump output is to visualize the simulation, maybe using OBIT or maybe VMD or whatever you have. So here you can see like I have used a custom. I usually use custom dump so that I can export the values I want to see or I may need. So in this dump custom, so this is the dump will be every 500 steps, and the name of the file is dump.lamps.strj. That is the lamps trajectory file, and then it will contain ID of the atoms, type of the atoms, and then the XYZ value, and then the Vx, Vy, Vz, that is the velocity of along X, Y, and Z, and the force along X, Y, and Z. And the dump will sort by its ID of the atom. So it will be sorted according to the IDs of the atom, like 1, 2, 3, 4, that way. Okay, so and dump, this is the name of the dump file, and then run niter. So you can see like these values, that is means like this is the variable I've mentioned earlier. Here you can see, so niter equals 3000, and I'm mentioning this variable here again. So that will be so this whole simulation will be running for 30,000 steps, and this is how we define variable. The same will be defined in maybe a Linux system, the terminal system. So these are final system that we're providing a fy, I mean like force along y -5 and a value along 1, and here is -1. In the upper group, all these values are 0. In the lower group, all these values are 0, and the temperature is 1. I'm sorry I wrote this 1 Kelvin, but it might not be a Kelvin. I'm sorry that I forgot that what is the value in Leonard. I'm not sure. Like Leonard Jones is unitless, so this should be 1, but this should not be 1 Kelvin. Okay, and the fixed NV, that is the total ensemble. Okay, so that is the thing. I'll be showing this part, but before that, I will show you how to run the simulation. I will run the simulation here, and I will show you the output. Then we'll go to this aluminum tensile loading simulation. But before that, do you have any question till now? I mean, if you have any question, you can ask me. Okay, let me, I think I should start the simulation and show you how it's running. Let me open it. So here is the simulation. So I have opened it in Visual Studio Code. You can open it with maybe Notepad or anything. I will provide you this file. You can run it by yourself and see what happens. So I'll be running this file right now and show you the result. So as you can see, I think you know this command, right? So the name of the executable and the in and the name of the file. You can see the name of the file is in the LAMMPS. So you see that the total simulation ran. It's a very small simulation, and as I'm using a Leonard Jones unit, so this is the total simulation. Now let me show you the output. I've already described all these things. The same thing here. The same thing, you have to write it all here. Okay. So let me show you the output using Obito. I'm sorry, it may take some time. So let me share.
I think.
Yes. Anyone have any
I think results are there, or still it is in running mode.
No. The results are here. As this is a very small simulation with Leonard Jones potential, so the results are very simple. That's why I'm showing it here. So this is the main simulation, and you can see that I opened the LAMMPS trajectory file, which I've created from the simulation. And so if I run the simulation, so you can see, okay, so that is from the first, you can see that the top layer has a force downward and it's moving, right? The top layer is moving this side and the bottom layer is moving this side. Okay, I will show you how. So to visualize this clearly, suppose let me select a particle. So let me just select a particle here and run it. See, so the top layer is moving on the right side. And now let me select a particle on the bottom layer and see it's moving on the left side. Same thing. Okay. And again, so you can see that the top layer has a velocity on the positive side is 1.2, which is close to 1. Actually, these values are very indefinite. It doesn't always give the exact value, but close to the exact values. And as I'm using arbitrary values, so it may not be the exact one, but you see it's close to 1. So it's almost 1.28. And maybe because of providing an NV fix, these values changed a bit. So its value is close to x is 1 and 0, 0, and the force is -5. That is 0, 0, and on the y it's -5. Similarly, if I select an atom on the lower side, you can see that Again, it's negative value and the force is 0, 0, as I showed you. Same, and the whole this system is moving. So I think everyone is clear about this. So if you have any question, you can tell me based on this simulation so that I can go to the next simulation. Does anyone have any question? And let me send you the input script. I will send you the input script in the chat box, I guess.
What we'll do at the end, we'll discuss.
Okay. So let me send the simulation file in the chat box. So I've sent the file as in.lmp. You can open it with Notepad or maybe if you have any code editor or something. So now we'll be doing an online simulation. That is actually because to run the aluminum tensile loading, it may take some time in my PC, but when I'm using a GPU from Google Collaboratory, so it will not take that much time. So I'll be using a GPU from Google Collaboratory and run this specific simulation. So okay, so let me open it with my browser and I will send you the links. I think this will be more like a workshop. You can open the file in your system as well. So let me send you the file. So I've sent a link of a collab notebook. You can go there. And now let me share. So the notebook I sent you. So this is the main notebook. So after going to a notebook, the first thing you need to do is the copy to your drive, or else you won't be able to edit those. So I'm copying it. I'm creating a new copy. You see that it's creating a new copy. So the first thing is go to that link I provided and go to the new copy, new link, the copy to drive. So when it makes a copy, the first thing you have to do is you have to go to edit and notebook setting, and then in the hardware accelerator put GPU. This is very important, or else you won't be able to run the simulation. So the first thing is here you can see edit, notebook setting, and go to GPU. And now I will install LAMMPS in this Google Collaboratory. So let me connect it at first. Connecting. I'm sorry, it's taking a bit of time, I guess. Just connected. And now I will just run this whole cell, these 6 cells. I will explain it, but just let me run it first. So the first cell is mainly what is my system in this collaboratory, that is LS CPU and NVIDIA SMI. So that is that it gives me the the GPU I'm using right now in this Google Collaboratory is free, so it will always randomize the GPU in your system in Collaboratory, so you don't have a very specific one. But if you use a Pro, like a Google Collaboratory Pro, then you can change these things, and it gives a 12-hour free session. So all you have to do is within 12 hours. And then I will run these commands. These are mainly created by Anton Gladke, who created these, pre-built LAMMPS, for Linux version. Not Linux, but for Linux distros. Okay, so that is what I'm doing. I'm just using those and importing LAMMPS and the OpenKey models. These are not actually needed. Just you can just write this one and run it. So that is what it's doing. I'm sorry, maybe I ran it twice. Okay, I guess. Then I'm installing all the LAMMPS table and LAMMPS table doc and everything. So this part mainly is installed. It takes a very small time. So every time you come to the Google Collaboratory, you have to install LAMMPS every time. Okay? Then I will write the files. So that is the first file is that aluminum alloy file. The EM potential, which I'll show you. I'm getting the EM potential from this NIST, I told you earlier that NIST.gov the potential, this gives a value of the this has a lot of potential repository. I mean, there are a lot of potential value force field files. So I'm just exporting a force field file here. So you can see that it's exported. Sorry, imported. You can say imported. So here it is, the file. And now I will run a LAMMPS, not run, I will write a LAMMPS file. Okay. So I want to write this file. So you can see that the file is written here. I'll explain it a bit later, but let me run it at first. So at first I'll run the file. So it started running. It may take like 34 seconds. It's very small. And compared to if I run it in my system with a single CPU, it may take like 30 minutes, but here it will take almost like 34 seconds. Okay, so here again, if I explain this, I think you already know these things like boundary condition, periodic, and I'm using a real unit, a metal unit, and a 3-dimensional boundary, and I'm using a FCC lattice, which is for aluminum, FCC with 4. Then its orientation should be 100. I mean, X it's 100, Y it's 010, and Z is 001. If you want to change the surface, I mean, if you want to cleave a surface, then you can change these values and change according to your need. And then I'm creating a region with 0, 10, 0, 10, 0, and that is I'm creating what can I say, 10 lattice unit direction. I mean, suppose 10 means here 10 means 10 into 4.05, so that is almost like a 40 in lattice unit. Okay, so suppose if I write here space box units box, okay, units box, that means this box unit will work on this unit box means it will work on the metal unit. But when I'm not writing anything, or maybe units lattice, writing unit lattice or not writing anything does the same thing. That is, it will work according to the lattice unit. Lattice unit is here, and the metal unit, the box unit is angstrom. And then again creating the whole box and the region, the same thing. Here I'm using a 1 atom type because there's only aluminum here. I think we already got the result. You see, it takes a very small amount of time. So here I'm using a EM value, EM alloy potential, and this is the name of the alloy file. Here you can see I've exported the alloy file name, the same one here, and then the name of the element I'm using, aluminum, and these are compute value to find the center symmetry and all that, the per atom potential energy per atom values, and then setting the time. I think I don't need to explain all these things because you already know this. I mean, you can just search for this. This is the center symmetry per atom for FCC lattice, and this will calculate the potential energy per atom. Then for the initial equilibration, so here will be 2 segments. At first we will equilibrate the system, and then we will use a deformation. As you know, for tensile loading, what happens in a uniaxial tensile loading, that we have a specific material, we have a specific system, and then we put a uniaxial tensile load in, I mean, like we provide a tensile loading in one direction, right? Like suppose maybe X, Y, or Z, right? Like in the mechanical what can I say, like in the real world examples, we also do the same. We maybe create a dogman specimen, and then we break it to find the stress strain curve. We are doing the same thing, almost the same thing here. Just we are not using a dogman specimen, but we are using maybe here we are using actually a block, and we are expanding the block to see how the atom reacts. So the first one is we are simulating, we are equilibrating the system at 300 Kelvin. So here is this 300 Kelvin because we are using a metal unit. In metal unit, the temperature is based on Kelvin. So 300, 300, and 301. So this is actually damping value. And the ISO 001, that means this is a 0 pressure. I mean, like the total pressure of the system is 0, which is very ideal. And the drag one is that there might be some oscillation. I mean, like LAMMPS can never get to an exact value. I mean, it always oscillates from the exact value. I mean, suppose you have provided a temperature of 300 Kelvin, and then it may not always give the exact 300 kilometer. It may go to 301, 302, or maybe 320. It will oscillate around a value that's almost like the same. So I'm using a drag command so that it will what can I say? It will be close to the oscillation value. I mean, it will be close to the exact value. So then the thermostyle, the same thing. So here we are using thermostyle, a different one, Lx, Ly, Lz, that is the length of the simulation box. Then pressure, Px, Py, Pz, that is the pressure on the simulation box, and the potential energy, the temperature. Okay. So we'll be running for 2000 time steps and unfix those. Then we will define a variable Lx, which will what can I say? Which will calculate the length of the x of the simulation box. That is the length again L0, where we are exporting the value, the final value of L0 to the temp value. So that is the initial length will be L0. So L0 is the initial length of the system that we know. And then see, we are resetting the time step as why we are, remember why we are resetting the time step. That is because this equilibration does not have anything to do with the deformation. Okay, so when we start the calculation, it will be very easy for us to start the calculation from 0. That is why we are resetting the time step again to 0. And again, we are using an NPT ensemble 300 at 300 Kelvin, and then along Y the pressure is 0, and along X also the pressure is 0, but as Z the pressure is 0, but along Y putting a strain, right? Specific strain. So we will be expanding the simulation box along Y so that we can get a strain value, and then from that we can export our data. So mainly will be the strain rate will be 0.001 per second. So that is what we did here. We changed the values to from I mean, like for metal it is picosecond. So just converting those values, and then 8, that is, so deform 1 x here, that is this deform value is deforming along x, and each time step 1 is means it will deform each time step, and x rate is the engineering strain rate, and then the strain rate value and the unit box. So here you can see we have used unit box. The unit box means it will work according to the unit of the metal unit, the box unit, rather than the lattice unit. That means the strain rate will be calculated as per the angstrom. I mean, these force will be calculated as per the angstrom. Okay. So box remap X. So it will remap all the atoms as per the deformed strain rate. Then these are just exporting the values. That what is strain? What strain is the difference of the final length minus the initial length, and by the initial length. Sorry. So that is what strain is, right? So that is what's written here, and then we're exporting the strain, and then the pressure along XYZ. So the same thing here. So why we did here like 10,000? That is just to convert it from bars to GPM. That's it. So the result will be gigapascal. And then this part is just to print out the results. So all these values will be printed in a file named output.txt, and it will not shown in the screen. This part is not needed actually. It will not be shown in the screen actually. So output.txt, and then I'm also dumping the values, and I'm getting the results as x, y, and all these values, the x, y, z, then the center symmetry values, then the per atom potential energy per atom values, and then the force values. Then I will modify this according to aluminum. So we know that the system is working with aluminum. Then these are the again the thermal values for this purpose. I mean, like for the deformation purpose. And then we ran the total simulation and done. So we run the simulation here. So these are the results. I think you'll understand the result here. So you see that for the deformation purpose, these are the results we got and done. So here you can see the strain rate starts from 0.0 something very low, consider it 0, and then starts with 0.01. We're getting values with 1,000. So it almost works with our very low quantity, like 0.001 and then 0.0015, like that. Okay, just I'm outputting the values here. When I will open this out.txt, you will see. So this is the main output file. So our next part is analyzing the data. But before that, I want to show you what out.txt is. That we exported the values, these values, right, from out.txt. So let's open it. So here you can see, if I expand it, see, so this is the string. Right? So let me show from here. So what out.txt is doing. Okay. So P1 value, P2, P3, P4. So this is the strain, right? This is the pressure along X, this is Y, this is Z. Okay, so actually the pressure along X and Y and Z should be very close to zero, okay, or constant. That shouldn't change much. So we don't have to, I mean, like work with these values, but rather our main focus is this two part. Okay. So we run the simulation here. Okay, wait, let me also download the dump LAMMPS so that I can show you this. It may take some time, sorry. Okay, when it's downloading, let me show you the analyzing data. So now we will analyze the data from out.txt. I think if you're familiar with Python, so I personally use Python to write data, to analyze data. So I'm just importing pandas and NumPy just to, I think if you know Python, you can easily read this. So just exporting the data, importing the out.txt here. And so these are just showing the values. And then I'm plotting the value. So let me run it. Okay, so here you can see that at first I built a software that is like I'm importing the values, then I'm putting the strain and the stress X. Okay, so and then stress versus strain. These are just the name. So the main work is here, and these are just the name things. That's it. And the X limit, Y limit. So this doesn't matter that much. So you see that it shows a very perfect stress strain curve. So it's already downloaded. I'll show you that stress strain curve. And you see that this is the ultimate tensile strength, and then it lowered. So that means it broke. That is what we know, right? So this is the elastic part, and then it broke. So we'll be calculating the elastic modulus from here. As we know that the tangent here is the elastic modulus. That is the ratio of the stress versus strain, right? So that is what we'll do here. We will fit the curve with a linear regression, maybe, or maybe a value of y is equal to mx, right? So that is, as we know, the y is equal to mx is the value of a value of straight line. So if we fit this curve with the straight line curve, then the tangent value will be our elastic modulus, right? So that is what we did here. We just imported a curve fit and then defined a function for linear line, I mean, equals to mx, and then fitted the curve here and then exported the value. So let me run it. Okay, so it gave me like 59.65 gigapascal. And now I'm exporting the fitted curve in this value. So here you can see I exported the data from 0.001 to 0.125. And why am I doing this? Because like suppose you see here up to this portion is almost straight, right? You can also consider this portion, but if you consider 0.15, the values might differ because there is a slight curve. So I'm just considering for the same value, I'm considering 0.125. And from somewhere, if you consider 0.05 to 0.15, it will almost give the same value, I guess. But let me show you. Let me change the values and let me run it. See, almost the same value. So the same thing. So it will calculate from 0.050 to 0.15. So there is a elastic modulus calculated from the graph. And then let me plot that straight line with our data. I'm sorry, it's okay. This is because I've limited the value from 0. It will be more like 0.05. So 0.05. Okay, so here you can see that the values are, so that these circles are actually the strain values. the values we got from the graph, the data from the simulation, and this line is the main the linear regression fit. What we did y equals from the y equals to mx. So we fitted the graph, and this is what we got. This is the value here. So okay, let me open the dump file. Okay, can you see the dump file? But let me reshare again, I guess. So let me reshare the dump file. So I've opened the dump file here. You can see so this is the main file. So just run it. So you can see that the file, the simulation box is expanding along along x. So this is the x direction, and it's expanding along x. From here you can also see it's expanding along x. At a certain portion, see there cracks. You see there's a 45-degree crack and forming. So okay, this is the part where the system failed. You can see started forming somewhere here. We can visualize it with the center symmetry values. So assign color, provide a color coding. So here you can see. So just finish. See that? Yeah, you can see clearly that the center symmetry is changing and the crack is coming. I mean, the system is failing. So I think that was it. That was the tensile loading simulation, and we also calculated the elastic modulus. So now, do you have any queries? If you have any query, continue. If you have any question, you can tell me regarding the simulations I've showed you right now.
Yes, yes. Now, students, is there any question? How to convert Vesta to lamps? Because in one of your video, you mentioned first we have to convert that into atom scale.
Yes, sir. So, sir, to convert uh, from Vesta to LAMMPS or maybe from other software, at first you need to export it to maybe a CIF or any relevant file, XYZ, any relevant file. Then there are two ways. There are multiple, but most commonly are like using an AtomScape or maybe use VMD directly. If you have any queries, then you can mail me, and I will also be uploading this video in my YouTube channel, so you can, I mean, rewatch it if you want, so that if you have any doubts, you can just rewatch it, and I think the doubts will be clear. Or if you still have doubts, you can mail me, and I will try to reply. So I think that's it. So should we end?
Is there any WhatsApp number is there with you? Are you?
I have WhatsApp number, but so I will mail you, I guess.
Okay, okay. I think.
I think if you don't have any question, you can just mail me your questions later whenever you find them.
Yes, yes. Is there any course or what you can say, like Coursera, NPTEL, is there in your study?
I'm not sure about that, sir, because maybe there. I'm not sure if LAMMPS does have any course or not. Maybe there isn't. I mean, the documentation is the best way to learn LAMMPS actually. I think actually the main thing is like LAMMPS has so many syntax. I mean, it has a lot of syntax, and each and every day developers are developing, not the developers, the researchers are also developing different codes for different kind of simulation. So to summarize all those is pretty impossible. And there might be some basic course. I'm not aware of that, but I think you can search.
Okay.
But if someone has a like the basic idea of molecular dynamics, the classical molecular dynamics, and the algorithm on how it works, I think they can pretty easily learn LAMMPS. Though the curves are a bit steeper, in the learning curves a bit steeper, but still, like if they, like try for some time, or maybe if they have, I mean, LAMMPS is more like the other molecular dynamics software like GROMAC and then those other ones. So you can use those. Oh yeah, and I forgot to mention, there is a book. I can suggest that. That is a book by Dr. Jungan Lee, Computational Material Science, and there are a lot of example of LAMMPS. You can follow that.
Okay.
And that also has some basic understanding, basic knowledge of molecular dynamics. And for the developing purpose, you can follow the book by Shafat Mubin, Extending LAMMPS, which I have a bit of a contribution, I must say, like a very small contribution, but still. So you can also follow that book, but that is a bit higher. There's a bit for developing purpose, but for simulation purpose, you may not need that. But I'd still suggest to know the backbone of LAMMPS. You may read that book if you want.
Yes.
I think Sarah has showed you that book in my website. You can go there and read that book. I think we can end if you don't have any question. Thank you, Anil sir, for inviting me.
Really, you gave very insights. You covered a lot of things, and specifically code. That 4 steps are there, and each and every step you have mentioned very nicely. And students, whatever our students are there, definitely use this video as well as whatever your YouTube videos are there. All that videos will be seen by our students in future, because whatever the projects will be there that are in line with this software or methods. And you explained very nicely, and definitely its output will be will get very soon. And with this, really, I am thankful from from our institute side. And personally, I thanks to you. You have given very nicely explanation to our students. And again, I am very thankful to my students also, because they have listened very patiently. And I hope they will utilize whatever the thoughts given by Abdullah ji. They will implement in their future whatever the research work is there, and they will obtain output from that. Now with this, once again, I am very thankful to Abdullah ji and all students. May I conclude here?
Yes, sir. Thank you, sir. Thank you for giving me this chance, and
Okay.
I hope everyone will have some profit from this webinar. Thank you.